Welcome back, everybody. In this video, we're going to talk a little bit more about transition state structures. So in previous videos, we've talked about kinetics and how we can use kinetics to define the energy of a rate-determining step or a transition state structure. But we haven't really talked about what those structures look like. Remember, we said that a transition state exists for a very small amount of time, right? It's essentially one bond vibration. So we don't have easy ways of spectroscopically observing them. Therefore, how do we figure out what that state might look like? And one way we can do that is through the Hammond Postulate. So the Hammond Postulate states that a transition state structure resembles the structure of the nearest stable species. Or minima. Right? So we're going to take a look at this and go over a few scenarios of what this means. This is going to apply to every reaction that we learn in the remainder of the course. So please try and remember this because it's going to be how we justify the structures of intermediates and some of the selectivity that we observe in reactions. So before we get into that, let's talk about how we draw a transition state structure. So we're going to take a really simple molecule and react it with some anion to make an exchange of X and Y. All right, so notice that we have formed a CY bond and broken a CX bond. So there are two bonds, one bond being made and one bond being broken in this reaction. Now, how this proceeds, we will get into in substitution chemistry, but let's say that this is a simple reaction, it happens in a single step, so we can look at our molecule So Y is going to come in and the lone pair is going to feed into this carbon. And as it does that, the carbon doesn't want to violate its octet, so it's going to kick off the other bond. So it's going to break that bond with X, giving the electrons from this bond here, the CX bond, to X. So as we're proceeding, Y is getting closer to the carbon and X is getting further away. So if we look at this as the reaction progresses, we're going to see that we start forming bonds for Y and we're starting to break the bond with X. Now we can indicate these with dotted lines, which are partial bonds. All right, and so as Y is starting to form a bond with carbon, it's losing that negative charge, so it's going to have a partial negative charge. Remember, we've seen this symbol before when we did resonance and we talked about drawing all resonance contributors as one structure. Well, here, Y is starting to form a bond, so it's going to share those electrons, and it's not going to have a formal negative charge anymore. And X is gaining the electrons. Remember, we showed the arrow here from the carbon X bond, giving those electrons, both electrons from that bond, going to X. So X is going to start gaining negative charge. All right, so this is what our transition state somewhat looks like. we have a bond forming and breaking. And out of that, we're going to get the following product. So a new bond formed to Y, and X has left. So this would be a rough estimate of our transition state. Now, what we use the Hammond postulate for is to figure out how much of the carbon Y bond has been made and how much of the carbon X bond has been broken in that transition state. And we can do this, again, by comparing it to the energetics of the minima. Remember, we want to put things in terms of physically observable species, or things that we can more easily identify. So, let's take our transition state and consider two scenarios. We're going to start with the reaction above being exergonic, or so remember, exergonic is a negative delta G, exothermic is a negative delta H, which means that it is product favored. All right, so here we're going to go back to drawing our potential energy surface. And look at our reaction coordinate. All right, so it's important to remember that while we define reaction coordinate as something very vague, right? It can mean anything from a rotation around a bond, if we're looking at conformers, to the making and breaking of bonds. Here we're going to look at the reaction coordinate along the, well, let's say Y, C, X. So we're looking at how much bond making and breaking has occurred in the CY and CX bonds. That's what's occurring on this reaction coordinate. So we're going to start by assuming that our starting material and our product, so this is starting material and our product. So we can see here that our product is lower in energy, meaning that this is a product favored species. So you'll often see transition states drawn where we just kind of loop these in, right? We just draw something. But in reality, what the Hammond postulate says is that because the product is lower in energy, it's going to be further from the transition state. Because remember, when we draw this line, this is going to be our highest energy state. So the transition state is going to be further away from the product than it is from the starting material, which means that for an exothermic reaction, the transition state is closer in energy to reactant. So And based on the Hammond postulate, because it's closer in energy to the reactant, it will look more like the reactant. All right? So it's going to sit somewhat closer to the reactant on our reaction coordinate. So it's going to be a little closer to that. What that means in terms of our transition state. So remember we drew this structure up here where Cx and Cy were both forming and breaking. Well, so our reactant, remember, has a full bond to X, which means that in our transition state, and I'll draw in the hydrogens. So our transition state for this reaction is going to have a shorter distance between C and X because less of the bond has been broken, because we haven't traveled very far on our potential energy surface to reach our transition state. So it hasn't had a chance to fully break or come close to half breaking that CX bond. Right? This will be longer, and the CX bond will be shorter, which means that Y will have most of the charge. And X will have very little of it because it's still sharing a lot of that electron density with the carbon. Okay, so this is an example of an exergonic reaction. Remember, the transition state is going to look more like the species it's closer in energy to. In this case, the reactants, which means that you're going to have a short CX bond. So we'll indicate that as our transition state. All right. So let's take another example. Let's say in this case, we have the reaction being endergonic or endothermic. Remember, endergonic is going to be a positive delta G, meaning that it's reactant favored. So here, and again, we're still looking at the CY, CX bond forming and breaking. So we're going to be looking at this reaction coordinate. It's the only thing that matters on this energy surface. So let's say that in this case, let's draw that one. Let's give us some more room. We have our reactants and our product is higher in energy. Now this is an extreme case that I'm just using as an example. It's often not going to be a large difference, but we're not drawing this to scale anyway. All right, so in this case, if we draw our transition state, remember that it's the highest point here. Now, because the products are higher in energy than the reactants, our transition state is going to more closely resemble the products. Which means that we would now be looking at let's draw it the other way. So our transition state will look more like our product. Meaning that if we draw our transition state out, we're going to see that we now have a very long bond to X and a short bond to Y. Because this will be mostly broken, right? So in the transition state, the CX bond is going to be much closer to fully broken, and the CY bond will be almost formed. And therefore, because that bond is almost fully broken, that means that the X has most of the negative charge on it. So this is the Hammond Postulate. It's basically there to help us describe transition states in terms of the minima around it, or things that we can observe. This will come in several different places in the remainder of the course, where we're going to look at energetics of reactions and try and understand the energetics of a transition state based on the energetics of the minima. So we'll try and figure out how high the barrier for a reaction is based on the stability of the intermediates that we're forming. Okay, so keep this in mind. We will go over these reactions. You don't have to learn a lot. This is going to be substitution chemistry right here. We'll get into this in about a week. But for right now, just try and understand bond lengths and energetics and what a transition state is likely going to look like based on the species around it.